Okay, so in this problem we have train tracks running east-west. So I've drawn a little diagram below. And we have a train on one track moving east at a steady speed of 20 meters per second. That's this train on the left. And it's approaching a second train facing it on an adjacent track, so they're not going to hit each other. That's initially at rest. And when the front end of the first train is 500 meters from the front end of the second train begins to accelerate westward at 1.4 meters per second squared. So I've drawn out a little diagram and I've defined that the front end of the first train is going to be our x equals 0 mark, and that means that the front end of the second train is x equals 500 meters. And you may define these differently. You could define the second train as x equals 0 and the first train as x equals minus 500, and you should get the same results. So first, let's write out equations to describe the position of each train as a function of time. So for train 1, x naught is 0 because of how I've defined the axes. V naught is 20 meters per second, and the acceleration is 0. We know that because the problem says it's moving at a steady speed. And so we can say that the position as a function of time is just 20 meters per second times t. So the position increases linearly in time. For train 2, it starts at an x naught of 500 meters. Let's call it at time t equals 0. The second train is at rest, so v naught is 0. But the acceleration is 1.4 meters per second squared, and it's accelerating westward, which we've defined as sort of the minus x direction. So it's minus 1.4 meters. The x position of the second train is given by 500 meters minus 1/2 meters per second t squared. Okay, and so we have the x position of train 1 is linear in time, and the x position of train 2 starts at 500 meters and then decreases quadratically in time. And so we find that the graph that describes both of these scenarios is this one, where this is train 1 and this is train 2. Okay. So the next part of the question says, when do the front ends of the train pass each other? And for that, we want to know, that means when are the two trains at the same position, right? And I've defined this x of t, assuming we're talking about the front ends of the train. So we don't have to worry about the fact that the train actually has some length to it. Let's just treat them as points. So these two are equal to each other when 20 meters per second t is equal to 500 meters minus 1/2 meters per second squared t squared. So this is an equation that is quadratic in t. And so let's move everything to the same side, and then we can solve using the quadratic equation. So 1/2 meters per second squared t squared plus 20 meters per second t minus 500 meters equals 0. So we can solve this using the quadratic equation, where this is a, this is b, and this is c. So t equals minus b plus or minus square root of b squared minus 4ac all over 2a. And this is kind of messy, but you can plug it into your calculator, and you should get that t equals either minus 44.6 seconds or 16 seconds. And we're going to pick the 16 seconds as the reasonable physical answer because we're saying that this problem starts at time t equals 0. That's when the second train starts accelerating. We don't know what happens at negative time, so that's not a reasonable answer. So we'll choose the 16-second answer. But if you're wondering what that second answer would mean, what we have here, we showed in part A that if you graph the motion of the two trains, they look something like this, right? If this is train 2 and this is train 1. And the quadratic equation doesn't know that we're only talking about positive times, right? The quadratic equation thinks we might as well be talking about equations like these that go on forever. And so it will find the two solutions when these two curves equal each other, and that happens here at 16 seconds. That's our answer. But it also happens here at minus 44.6 seconds. And so obviously we want to choose this positive answer. Okay, so it should be 16 seconds.